All right, hey everyone, I'm Jesse. I'll be talking to you about the protruding fossil in the inner halo of our galaxy. Um, so I have a lot of collaborators, namely the H3 survey. It's mostly Charlie Conroy, Benjamin Johnson, Phil Cargile, Rohan Naidu, and so on and so forth. So there's a long and rich history of studying the stellar halo of the Milky Way that I cannot go over possibly within a minute. So let me give you the most recent sort of new halo picture that we have uncovered from the Gaia revolution. So there are sort of two distinct phases in the stellar halo. We have the inner halo within 20 kpc, where it is entirely dominated by this one merger event called Gaia Sausage Enceladus, GSE from now on. And then beyond that, it's a little more mystical because there's a lot of unresolved debris from former mergers that we don't quite know yet, but we sort of see signs for it in phase space. So to recap again, the inner halo we now believe to be mostly comprised of stars from this GSE event. This is just showing you how much the inner halo has been studied by past groups. A lot of them model the inner halo or the mid halo as a double break power law with some flattening parameter and some breaking radius. And they all share a common property in that they fit a one-dimensional RQ model, so aligned with the disk that has some flattening out to maybe, say, 90 kiloparsecs. So if this has been done so many times before, why do we have to do it again? That's when H3 comes in. Also, this cake was made by our dear colleague, Claire Lamont at Harvard, to observe our postdoc's birthday. So H3 comes in because we have Gaia, but Gaia doesn't have radial velocities for a lot of stars in the regions that we're interested in, namely 20 kiloparsecs and out. So H3 targets these Gaia stars using their parallaxes as prior information as a sample selection. And then we take stellar spectra to obtain radial velocities, metallicities, and alpha abundances of these star particles. The resulting catalog is that we now have a catalog of halo stars where we have 6-dimensional plus chemical information, which means we can actually begin to untangle the inner halo and fit individual substructures in our galaxy. So, as I said before, the inner halo is mainly comprised of GSE. So the immediate question is, what does GSE look like in our data, and what does that reflect like its true shape? So we can sort of think of this as a tiered level question. The first level of question we can ask is the basic things. How big is it? How massive is it? What does it look like? What's its orientation? And from that, we can progress on to the higher level questions to be tackled, such as what does this imply about the Milky Way potential? What does this imply about dark matter dynamics? So on and so forth. Right, so to answer the first part of the question, what does GSE look like in our data itself? As someone pointed out in an earlier talk, there is a chemical signature. We believe that due to its accretion history and its star formation history, it has a distinct sequence in the alpha FEH plot, bottom right panel. So the gray plots or the gray dots are the entire sample, and you sort of see a bimodality in the upper side of the panel and the lower side of the panel. This is indicating the thick disk and then the GSE sample. And then we see another signature in eccentricity space or dynamical space. On the bottom left panel, we see that there is a cluster of stars that have super high eccentric orbits. This was originally how GSE was detected, so we also applied that selection cut to our GSE sample. So just to summarize that again, we have two criteria that we select GSE stars on: its eccentricity and its chemistry. And with these two sort of broad stroke cuts, we can recover like, a lot of GSE stars within our inner halo. Now, but the second part of the question, which is what does GSE actually look like in the galaxy, is a bit more difficult to tackle because we have a selection function and a window function through which we observe the galaxy. We are unfortunately not located in the galactic center. That'd be really cool. But we look at it from this sort of weird point of view from outside of the disk. And without going into too much detail, I like to think of this selection function as a 3-step process, where first there's a spatial big cut because we were looking at particular line of sights. And then within that line of sight, we have some sample selection of giants or BHB stars or RLI that we want to observe. And then lastly, even within that stellar sample, on a given night observing, we only get so much quality data, right? So there's going to be some limiting magnitude dependent on the weather condition on that day. So all that wrapped up into a page of math is the following. We model it as an inhomogeneous Poisson point process. I'm just throwing it out there in case someone asks later on. But the last two slides were basically my last 2 years. But it's time to move on to the next. So we have this grand formalism that we propose to say, we can now measure the true shape of GSE. So how do you back up that statement? We do so by creating these mock catalogs generated from true samples of GSE, pass it through the whole H3 selection function, and get an H3-ified mock catalog, and then try to see if we can recover the true parameters. Right? So in a pictorial sense, this is what we're trying to do. Given a set of true shape variables of GSE, we H3-ify it, we pass it through the full selection function, and then see if our resulting fits, depicted as the corner plots, match up with the orange lines, which are the true parameters. So the diagram on the right is like the best case scenario where everything is unbiased, the accuracy is pretty good, we're happy. So this is what we actually do. It's a 7-dimensional model, which means it has some overall normalization. There's an inner power law slope, there's a breaking radius, there's an outer power law slope, there's a flattening parameter, and what is most novel is that there are two rotation angles at which we can rotate this structure with. So yeah, as you can see, most of these corner plots look pretty good. They are unbiased, they are pretty precise. The two sort of corner plots that might raise your eye are the breaking radius and then maybe the pitch angle. It's hard to see here, but you should note that these are off by 1 kiloparsec. And that is a pretty good place to be in the sense that we're searching between like 8 kiloparsecs and 50 kiloparsecs. Same with the pitch angle, it's off by maybe half a degree of what we put in. Right, so just to back up a little bit in the last these 2 minutes, what do we set out to do? We said, we know the inner sample, the inner halo is comprised of GSE stars. We want to be able to measure it, and we want to be able to verify our measurements. So that is exactly where we're at. So all there is left to do now is to apply this to real data and see what's up. So this is the result. Oh no, I don't know why that is so blurry. These are the two main results. But so on the left plot is our fit of the GSE sample, and the right side is the fit of like the total halo sample, which is more comparable to prior literature. The punchline is this. If we limit our sample to GSE stars, we obtain a prolate, tilted, and azimuthally rotated structure. Meanwhile, if you fit the whole halo, as whatever that means in this hierarchical sense, we recover the prior results that have an oblate spheroid that is perfectly aligned with the disk. So even without going to the full MCMC fits, we were able to already see signs of this tilt and this angle in the data. So basically what's happening is the following little cartoon that I draw. We're observing a rugby ball shaped thing that is pointing upwards from the plane. So we should be able to see more stars in the galactic north and the south. So on the right are two examples of a mock halo that doesn't have a tilt and has a tilt. And then on the bottom panel is the real data. And as you can see, indeed, we do see this overdensity of stars in the galactic north, which is a telltale sign of this tilt. Even more fascinating is the fact that retrospectively, we're able to find evidences of this tilt in prior literature, particularly in the RLI sample. I won't go too much into in-depth as of time, but this is pretty exciting stuff that you can sort of look back on these figures and sort of visually fit a line and see that there is a non-zero tilt to these data sets. So the key takeaways are the following. One, H3 is really cool and it's awesome. We have expanded the sort of six-dimensional phase space world we live in, thanks to Gaia, out to 50, 60 kiloparsecs. Using that, we actually fit or measure the shape of a particular merger remnant that we believe to be occupying the inner halo, and find that it is, contrary to prior literature, prolate and tilted and pointing out from the plane. And yeah, that is the main key takeaway. And I will be happy to take any questions if you guys have. Thank you. I'll put up the key takeaways.
Very nice, Jesse. So, yeah. So if I got this right, it's tilted, right? So it's above the plane here, but it's below the plane on the other side of the galaxy, yes?
Exactly.
I'm just trying to get the 3D. And is it rotated?
It is rotated with respect to the galactic x-axis.
Okay.
So just the line of sight between us and the galactic center.
Good. So I guess what I'm wondering is, do you have enough data that you can, that the deviations from a prolate fit are interesting? You know what I mean? If it's not just simply an ellipsoid, can you tell us, say anything about that?
That's a fantastic question. So there's always the issue of overfitting your data, right? However, we do have reasons to believe that this merger remnant should not be actually an ellipsoid for either triaxial or shell-like structures out beyond 30 kpc. It's just really hard to say with maybe like 5,000 stars in your sample. In future surveys, maybe with Sloan 5 or with DESI, I think that would be a really interesting thing to look into for sure. Deviations from just your even like three-dimensional model, or rather having radial. You can imagine a situation where you have different pitch angles for like different radii, right? Yeah, that's a good question, but no, not in our data set.
That was a nice talk. I mean, I'm really curious what happens if you start playing with your selection boxes. Mm-hmm. You select chemically and kinematically, I believe, right?
Yes, sir.
So imagine, you change your selection a little bit. I'm very curious. Have you guys done tests where you change your selection and see, does it still come out prolate and tilted?
Yeah, no. So that's a fantastic question. That was the whole exercise of the right panel. So we remove the chemical selection, remove the eccentricity selection, and we raise the spatial window out to greater than 4 kiloparsecs, which is sort of traditionally what we regard as like the halo. And if you fit those stars, you obtain an oblate spheroid, the vanilla oblate spheroid.
So I guess, I'm still, I guess my question really is it possible then to start changing the selection and find other things that aren't GSE?
Oh, yes. So we have like 7 substructures we want to fit after GSE. So if that's what you meant, yep. Exactly, yeah.
Okay, great talk. Thank you. I was just wondering, in your final selection of GSE, do you have any idea how much contamination is in that sample just from these outputs of your selection function?
Yeah, so that's actually there's a whole paper about it that our group wrote led by Rohan Naidu in 2021. So our selection of GSE is actually not like just plain eccentricity and chemistry. It's also required to not be part of any other substructures that we identified in ELZ space, in other phase-based dynamics. So there certainly could be contamination from, for example, the high eccentricity tail of the thick disk or the low metallicity tail of Arjuna and things like that. But we think the contamination is pretty small. And in fact, the next step is to fit the so-called in situ halo or the splash disk, where we're actually looking at the contamination of the thick disk in the halo and see what that looks like. So even the contamination itself is pretty fun to look at.
Thank you. Yeah, great.
So in your all halo stars, how many? What fraction of those stars are out like past 30 kpc?
Oh, past 30 kpc is a very sizable fraction. I would say not like half, but at least a quarter.
Have you thought at all about what the LMC does to that? Not to be like hammer and nail.
No, that's a great point. I actually don't know. So like the lore is that the orientation that we find is in the direction of the LMC and SMC. So maybe there was like this giant cosmic web that feeds everything into this. I'm not going to continue the sentence, but yes, that is a fantastic point that we should think about. And in particular, I haven't thought about what imprints it will leave in the velocity space of these stars. So yes, we should chat later.